Well, good evening, everyone. I show 6 o'clock Central Time, so we'll go ahead and get started. Thank you for joining us for our first aviation weather workshop. My name is Jonathan Leffler. I'm the Warning Coordination Meteorologist at the Aviation Weather Center. This workshop is a joint effort between 3 aviation offices in the Kansas City area. AWC, we have the Center Weather Service Unit in Olathe and the Weather Forecast Office in Pleasant Hill. I'd like to give a special shout out to the KC Aviators who have partnered with us in this endeavor. Special thanks go to Chris and Evan for helping us get this off the ground, and really appreciate their support. A couple of housekeeping items as we get started here. Because we've got a pretty large group of people attending, already up to about 115, we've got everyone's microphones muted so we don't have any additional background noise. But we do have the chat room open, so if you'd like to ask a question, just drop it into the chat. And we've got a couple of folks monitoring that, and we'll do a couple of Q&A sessions. We have a pretty great lineup of presenters this evening. We've got a session for organization, will be session 1, and then we've got, we'll transition over to winter hazards in session 2. So again, thank you for joining us this evening. We hope you enjoy this workshop and that you find this information very useful to you, make you a little bit smarter when you go fly. And with that, we'll get started with our first presenter, Joey Welsh.
Well, thank you, Jonathan, and good evening, everybody. Thanks again for joining us tonight. I know it's your evening, but we appreciate your time. And hopefully you can take some good tips away from the presentation here. I'm Joey. I'm a AWC meteorologist. I've been here not very long. I got here in February of this past year. So still learning the ropes, but before that, I was at the Weather Forecast Office in Pleasant Hill, Missouri. We served the Kansas City area. A lot of northwest Missouri into central Missouri, a tiny sliver of eastern Kansas. And I was there for 6 years, and before that I was in the private weather sector in Houston, Rockwell Collins. I think they have a new name now, but I was an aviation meteorologist there for about 1.5 years right after I graduated school. And going back further from that, I was an in-flight refueler in the Air Force on the KC-135, and that's what really got me into weather, strangely enough. I was already into aviation, but I was at McConnell Air Force Base in Wichita, Kansas. So go ahead and slide there. So we'll take a quick look at the WFO operations, the Weather Forecast Office operations as a whole. There are 122 offices spread throughout the CONUS. And we'll take a quick look at what each office does. You'll see on the map what looks like tiny puzzle pieces. This is basically the area of responsibility for each office. The one I worked at was in Pleasant Hill. They're in the middle of the country. And you can kind of see where you're at and what office serves you. And feel free to visit their website, their social media outlets, and get up-to-date weather information. They do provide more insights into weather forecasts and timing and specific hazards, more so than a weather app can do. So if you go to weather.gov, that's where you'll see a map of the US. You can click on your particular area or click on your zip code and basically get a very tailored forecast. So there's a ton of information. We don't have time to go through it all, but we'll kind of show you what we do as a whole in the Weather Service from the Weather Forecast Office perspective. Slide. So typically at each office there are 2 forecasters on duty, and these individuals are on duty 24/7, 365 days a year. Staffing does increase during severe weather events, but there will always be at least 2 forecasters on duty serving in one of 2 roles, which are interchangeable. Everybody's trained the same, and you can switch in and out as you please. The first of which is a forecast desk, basically in which the forecaster will produce a 7-day forecast among a variety of other forecast products, which we'll discuss here in a little bit. The other and relatively newer role is that of the impact-based decision support desk, responsible for basically communicating the forecast to the government, to media partners, and to the general public as a whole. Slide. So in the IDSS communicator role, that forecaster is taking weather observations every 6 hours. They're answering phone calls. They're updating forecast graphics that are issued on social media and more official graphic products that are issued to government partners available on our website. During significant weather, however, they are conducting interviews. Not all the time, but a lot of times news crews will come to the office, or they may catch us during a tornado survey, things like that, where we'll conduct an interview and give critical updates to either ongoing weather hazards or things that have happened, in the recent past. A lot of times they will staff command centers on site for big events, for example, during hurricane events or even during annual events like air shows. I know when I was at Pleasant Hill, we did a lot of NASCAR activities at the Kansas Speedway. One of the other big things we did was the Missouri State Fair each year. And there are a lot of cases where severe weather was coming in and there were ongoing concerts, and we would provide critical updates to decision makers. And sometimes they would have to cancel or delay major activities, and not everybody was happy, but we were there to protect life and property. So it's a pretty new thing that we're doing, but it's well received, and we'll continue to do that in the near future. Slide. The other forecaster on duty produces the routine forecast that goes out to 7 days. They also provide aviation forecasts in the form of terminal aerodrome forecasts, or TAFs as you know them, and we'll look at that here in detail in a bit. They also produce fire weather forecasts, highlighting conditions favorable for wildfire spreading, flood forecasts, flood warnings, severe weather warning operations as well. Again, during severe weather, staffing is typically beefed up with at least one forecaster on radar issuing warnings. There are others who take storm reports. Some communicate with the radar forecaster on storm trends. Some issue the routine forecast products that still need to go out even during severe weather operations. And finally, there's a coordinator who kind of oversees staffing needs. Usually that's a manager, but there's a lot of cooks in the kitchen during severe weather operations. We can have up to 6 to 8. During major events like hurricanes, those areas can be staffed up even more. But at the very minimum, there's always 2 forecasters on duty. Slide, please. So we'll take a brief look at TAFs and how they can serve you. Each office issues forecasts for specific airports, generally for a 24-hour period. These are updated at least every 6 hours, and more often if conditions change rapidly over a short amount of time. So if we look at this example here in the upper left, this is for Kansas City International. You can find on each line of the forecast basically wind direction and speed. Visibility is next, ceiling heights, which are your cloud bases, weather types, and low-level wind shear if it's present. Each subsequent line represents a change in flight category, or the addition or removal of weather, and any significant change in wind direction and/or speed. So we send out the forecast every 6 hours, but we may adjust the forecast 2 or 3 times in between forecasts. So we want to make sure you guys get the most up-to-date forecast as we can possibly give you. And we also keep in mind category minimums, which do vary depending on each airport you're located at. Slide, please. So along with the TAF itself, the forecaster will write up a brief discussion, basically providing a synopsis of the forecast along with any uncertainty in that forecast. So you can kind of get your insight into what the forecaster was thinking when they issued that TAF. These are updated the same time we update a TAF. Maybe not so much if we do a quick amendment, but at least every 6 hours these are going to be issued. They're tailored to aviation needs and are typically short enough to be read during radio communications. And you can find the area forecast discussion, or AFD as we call it, on our webpage, aviationweather.gov, underneath the forecast tab. There you can kind of see it above Montana there. If you click on that forecast tab, you'll be able to see a drop-down menu, and then you'll see the option to select aviation forecast discussions. Slide, please. And that concludes the weather forecast operation side of things. And next up is Chelsea Kenyon at the City of BSU.
All right, thanks, Joey. My name is Chelsea Kenyon. I'm at the Center Weather Service Unit here in Kansas City. We're located at the Air Traffic Center in Olathe. And we are kind of the middlemen between the local aviation forecasters at the forecast office here in Pleasant Hill and the national forecasters at the Aviation Weather Center. So we kind of fill more of a regional role. And so next slide, please. We'll kind of detail how this all works. So all of the Center Weather Service units, or CWSUs, are co-located with the Air Traffic Center. So we actually work with the air traffic controllers. In fact, I sit next to the air traffic controllers every day. So part of our job is to provide them with forecasts, with any kind of lead time on any particular problems that may be coming their way. Say thunderstorms are about to hit Chicago, or thunderstorms are going to be blocking a large portion of our airspace, severe turbulence moving in out of the Rockies, mountain waves, any of those kinds of things are things that we're looking for and trying to advise the air traffic controllers about them so that they can have a plan in place to make sure that they can get the volumes of air traffic around those hazards. So as you can see there, Kansas City is right smack in the middle. And we have a lot of neighbors around us, so we do a lot of collaboration and coordination with our surrounding centers. We feed Chicago all day long, so that's a big part of what we do. So there are days when I'm actually more focused on Chicago weather than I am on Kansas City weather because it's such a big impact to our operation. We do a lot of work with Denver and Dallas-Fort Worth. And then on the midshifts, the overnight hours, that's when the cargo operations are going. So we deal with Indianapolis and Memphis quite a bit because UPS and FedEx fly through our airspace from the West Coast to get to those airports at night. So you can see on the inset map there, that's kind of a picture of our low altitude sectors. So the trails area is right around the Kansas City area. So that's where we are. And so when you take off out of the Kansas City area and you're talking to Kansas City Center, you're going to be talking to the trails air traffic controllers. So and they're all good. I can give them a thumbs up. Next slide, please. So you might wonder why we are actually with the air traffic controllers instead of in our own office. We've actually been doing this for over 40 years. We started in 1978 as a response to an aircraft accident that happened in Georgia. And what had happened is the flight took off. I think it was from Atlanta going to like Birmingham. They went through some weather, but it wasn't too bad. On the return trip, it had formed a complete squall line. And they didn't realize how bad it was going to get. And they tried to go through the line and lost both engines, crashed, broke up, and there was a significant loss of life. And one of the things that the NTSB determined after that investigation was that the air traffic controllers at the center needed more expertise at their disposal to know when that line of thunderstorms was going to become too solid to get air traffic through. So that's when the CWC program was initiated, and we've been right there in the thick of it with the air traffic controllers ever since. So we've been doing this impact-based decision support kind of thing for 40 years. And we take great pride in the fact that we can help them keep the airways safe. Next slide, please. So we are actually there only 16 hours a day, even though the center is open 24 hours. We don't work overnight because that's mostly cargo. They have their own meteorologists, so we try and give them a good briefing before we leave and hope they're not mad at us in the morning. But briefings, we brief people all day long. So we have some scheduled briefings that we do throughout the day to let controllers know what to expect for their shift, the traffic planners to know where the problems spots are going to be. We also do a lot of on-demand briefings. So anytime things are coming up, especially during the thunderstorm season, anytime anybody needs to know when is that hole going to close in between those two cells, what time is that going to hit that airport, how bad is the turbulence going to be, we answer those kinds of questions all day long. So we're there in case something happens and they need that information right away. We also do a recorded briefing 3 times a day, and that's for the air traffic controllers themselves. Before they take an operational position, we want to make sure that they know about the weather and what to expect for their shift. So all of the center air traffic controllers view that, and we also provide that for the terminals that are underlying our facility. So Kansas City TRACON at the tower, St. Louis TRACON, Wichita, Springfield, all of those controllers are seeing the same briefing. So they all get at least a basic weather understanding before they start controlling traffic for the day. We do a lot of collaboration as well, down to the local level with the forecast office. So we actually collaborate on the TAF for Kansas City twice a day at least, sometimes more. And then we also do that for St. Louis. And we are available to any of the forecast offices if they need a little extra aviation knowledge or have a question about how something might impact their area. We also collaborate upward to the national level with the Aviation Weather Center and the meteorologists at the FAA Command Center in Washington, D.C. So that's especially important during thunderstorm season when we're all trying to figure out how to get everybody from point A to point B through a massive line of thunderstorms. We need to make sure we're all on the same page. So being able to talk to them and making sure we're all telling the same story to the controllers who have to make decisions about that. We want to make sure that everybody understands how we expect it to play out. The one product that we issue is the Center Weather Advisory. That's the only public product that we put out from the center that you would actually see as pilots. And that can really be for anything. Most often it'll be for thunderstorms, but it can also be for turbulence, icing, IFR conditions, anything that's not covered in another advisory, or if we want to bring enhanced awareness to something, say severe icing and freezing rain. We could issue that on top of an airmet for icing to show that there's an enhanced risk in a particular area. So we kind of have free reign to make that product be whatever it is we need to be. It's our Swiss Army knife. We also provide a lot of graphics and forecast products for the air traffic controllers within our facility and the terminals. So we do a lot of graphics, but you won't see them unless you go onto our website, which is weather.gov/DKC. And you have access to all of that on the web. So you're free to look at that at any time. And you can also see our recorded briefing there as well. During the thunderstorm season, we also participate in what's called the TCF chat. So that is the Traffic Flow Management Convective Forecast, which is an acronym within an acronym. And so we do that from March through October. Every 2 hours, we get into a chat room. I think the AWC folks will talk about that a little bit later, but that's mainly a thunderstorm season thing that we do, but that becomes the basis for the air traffic plan for the entire national airspace system. So we are able to contribute in that way and make sure that how things are evolving in our airspace are represented. So that's it's kind of nice to have a little bit of a say in what happens at the national level. We also do a lot of training for the air traffic controllers. A lot of it is seasonal. We also do kind of an introductory weather session with new controllers as they're coming out of the academy. So we have a lot of training ongoing. And unlike the forecast office, we work by ourselves. There's just one of us on shift at any given time. So if it's going to be a busy day, it's on us. And if it's going to be a slow day, we're going to enjoy that. So thunderstorm season is really the busiest time for us. We don't pull in extra people when we know it's going to be busy. We just prioritize our duties. Next slide, please. So we wanted to kind of show this, and you can probably pull it up and go ahead and play the video here. This is just an example of how air traffic flows through our airspace. So Kansas City is kind of the long skinny one there in the middle, and the little tadpole looking things are actually airplanes with the tracks on them. And so you can see, I think this starts fairly early in the morning, so it's slow, but then you can see as traffic picks up throughout the day, and there's a little bit of weather there. So you can see how they go in and around the weather, what the flows are into Chicago, into Dallas, down into Denver as well. So those are kind of our major 3 airports that we feed all day long. We also have the transcontinental flows. So those are going to be the West Coast to East Coast and East Coast to West Coast flows. That has taken a significant hit during COVID for us because the East Coast, there's no business travelers, so it's been much, much slower. But those regional flows into Dallas and Denver and Chicago have really kept us busy. So there are some days when Kansas City Center is actually busier than New York, which has been kind of an odd thing for us. We also do a lot of ski country routes during the wintertime, heading up to Aspen, Eagle, those areas, and then we handle a lot of Atlanta traffic down into Florida as well, all the snowbirds heading south for the winter. So those kind of routes are going to still be there, I think, for this winter. So, but you can see how they have to kind of shuck and jive around the areas of thunderstorms. You don't want to be the controller sitting at the end of that line, having to handle all the deviations around the end of a line. That can get really, really busy really quickly. So it's my job to tell them where that line's going to stop, or if it's a solid line, if there's going to be a hole anywhere in that line, it's my job to tell them where it is so that they can prepare for that. So hopefully those controllers ate their Wheaties that day. But you can see how busy we can get there in the middle of the country, especially when the weather is blocking other places. So a lot of times it can funnel them right into us. Sometimes it can actually keep them out of our airspace. So weather is really important to the air traffic controllers in terms of how busy we're going to be. So that's just one example, and I think now I'll turn it over to Amy.
Hey, thanks, Chelsea, very much. A reminder, if you have a question that you want to ask, go ahead and put that into the chat, not under the questions board, but under the chat on the right-hand side, and make sure that you have it set to the entire audience so we can all see the question. And then during the question and answer session, we'll be able to share them and answer them for you. So my name's Amy McPherson. I am a senior meteorologist at the Aviation Weather Center, and I've been here for about 6 years in Kansas City, Missouri. Prior to that, I've been a forecaster at weather forecast offices in Washington, D.C., and California, Minnesota, South Dakota. So I've been all over the country, and I've been very fortunate to be able to do that with my career and be able to experience all sorts of types of weather and become sort of a weather expert of you know, anything from marine to tropical to and now to aviation, which I really enjoy. Okay, next slide. Okay, first off, the Aviation Weather Center is kind of our national scale perspective of en route aviation weather forecasting. And then we also have an international branch as well, which we'll get into. A little bit about the history of the AWC. Here in Kansas City, initially the Aviation Weather Unit from the Air Force joined what was then called Severe Local Storms, or CELS, which is now called SPC, or Storm Prediction Center, and then also the Kansas City Weather Bureau office in Kansas City, downtown in the Federal Building. And that is now the Weather Forecast Office in Pleasant Hill. So then in 1978, the Convective Sigma unit was established, and that was also in response to that same airline crash that Chelsea referenced back on April 4th, 1977. So that was, again, in response, and the pilots, the onboard radar was not able to see the solid line of convection that they were headed towards. They thought there was a hole that they could get through, but there was not. And so they established the Convective Sigma units so that, you know, they would have more resources to check up on whether or not it was safe to fly through a convective area. And then in 1982, the National Aviation Weather Advisory Unit was formed, and we actually have a forecaster still that we work with at the Aviation Weather Center that was there when the NWS, as he said it's pronounced, was formed. He is still working rotating shifts here at the AWC and has been since 1982. And then in 1995, the National Severe Storms Forecast Center did become the Storm Prediction Center, and then NWS becomes the Aviation Weather Center. And then finally it moved to our current location, which is closer to MCI Airport, and we are also co-located with Central Region Headquarters and the National Weather Service Training Center in this building there. Okay, next slide. And November 4th, 1992, it was written into law that we shall be established in the Kansas City, Missouri area, the Aviation Weather Center. And so we will continue to be a part of Kansas City's future. And that picture there is a bunch of us that, you know, are current employees there at the Aviation Weather Center. And that was right after the Chiefs won the World Series, and we're all excited, but before the pandemic started. So. Okay, next slide. So we have two branches at the Aviation Weather Center. We have the Domestic Operations Branch, and that consists of 5 desks. There's a desk dedicated to convective SIGMETs, one to TCF, which again is the traffic flow management convective forecast, one for the turbulence, and one for icing, and one for clouds and visibility. So for domestic operations, we're talking about the CONUS, the lower 48, and the surrounding nearshore waters or coastal waters. What we do on these desks is we issue SIGMETs, whether for convection or turbulence or icing or blowing dust if you're on the IFR clouds and visibility desk. So those are our aviation warnings. And then we have advisories and forecasts that we do as well. So every 6 hours we issue a new set of AirMets, which is our sort of advisory, a little bit lower grade than a SIGMET, but still areas of moderate or greater hazards. And then we do have the TFM convective forecast, which is the TCF. And that's more of a planning convective forecast for national traffic flow management. So that's used on a national scale, and then sometimes more on a local scale if thunderstorms are affecting traffic coming in and out of major airports. And that again runs through March through October during the more active convective season. And then finally, we also do a low-level significant weather graphic, and that has 2 snapshots at 12 hours out from the current time and then 24 hours out from the current time. And that shows areas where we're expecting low-level turbulence, IFR and MVFR conditions, and then also the current or the freezing levels at that time at 12 hours and 24 hours out. We collaborate a lot. We're constantly on chat with our partners. That includes the CWSUs. So we're chatting with Chelsea a lot, and also meteorologists at airlines, and also the FAA Command Center a lot. We're chatting with them just so that we make sure everyone's on the same page. We're sending the same message out, a consistent message that you as the user can get and understand clearly what we're trying to say and what we're trying to warn about. Okay, the next slide. Is it working? There you go. Okay, and then the other branch at the Aviation Weather Center it consists of 3 desks, and that's the International Operations branch. We have the Tropical Desk, the SIG Weather North Desk, and the SIG Weather South Desk, which are global graphics desks. So first with the Tropical, they issue SIGMETs for much of the North Atlantic and also much of the North Pacific, all the way out to boundarying areas of Japan's airspace, and then also our cohorts in Honolulu and also Alaska. So we're coordinating with them a lot out in the North Pacific. But we issue SIGMETs there for convection, oceanic SIGMETs for convection, turbulence, icing, volcanic ash, and tropical cyclones. And then for as far as forecasts for the tropical desks, we also write text area forecasts for the Gulf and the Caribbean, the Gulf Caribbean. So those are just written out text of information, especially useful for the tourist industry there in the Caribbean, and also for helicopter paths in the Gulf with the oil rigs out there. And then for the global graphics desks, we have 2 forecasters, one that takes care of the Northern Hemisphere and one that takes care of the Southern Hemisphere. And they are drawing charts for 24 hours out, mainly for transatlantic flights. So 24-hour forecasts for jet streams, convection, turbulence, tropopause heights, active volcanoes and tropical cyclones. So again, and so mostly high-level type of weather hazards for transatlantic flights. And then also with the Global Meteorological Services, we are coordinating every day. We have a chat up with the UK, Canada, Brazil, Australia, New Zealand, Guam, Hawaii, and Taiwan. So we are constantly coordinating our global weather graphics and our global forecasts so that, again, we are sending consistent messages, and then we're also ensuring that we have seamless transitions of SIGMETs from one airspace, let's say the Japanese Meteorological Agency as an area of convection is coming into the North Atlantic airspace that we take care of, that we are coordinating with them so that there is a seamless transition and that that weather is warned for those flights. Okay, next slide. We have the next slide. There we go. And then a couple of other, so we're a national center. There's a couple other national centers that you're probably familiar with. Oh, we went one too many. Let me go back one slide. There we go. The Storm Prediction Center, you're probably familiar with. Every day they have outlooks, 24-hour outlooks for what they expect for areas of severe weather for the day. They also are the ones that issue the tornado and severe weather watches. So they have those hazardous weather outlooks. They have a whole plethora of information that you can look into as far as, you know, just really getting into the nitty-gritty of mesoscale guidance for severe weather to initiate and grow, and also a plethora of other hazardous weather forecasts. But I know a lot of people go there just to see for an overview for the day of where, you know, where convection and where thunderstorms are expected and where's the most severe thunderstorms expected for the day. Another great source is the Weather Prediction Center, where you have weather analysis and forecast products. So you have, this is more surface-based, where you have your fronts and your high pressure and low pressures and troughs all analyzed at the surface. But also you can find there the upper level charts. And then you can also see that they have areas of precipitation that are expected during that time. So you can see future analysis of the fronts and the precipitation on their website as well. I believe we have all of that linked on our website, aviationweather.gov as well. Okay, next slide. All right, so at the Aviation Weather Center, we are very dependent on pilot reports. Those are things that really help us decide whether or not our forecast is going in a good direction or not. It's a great tool for us. So while we have satellite and we have the model data and we have the radar, and we can really make a really good assessment of what's happening and make sure and have our forecast out based on that information. When we get an actual report that turbulence is happening in an area where we have forecasted turbulence, that really gives us the confidence in our forecast and to keep going. And if we get something outside of an area that we have not forecast, then that might, you know, have us look into it a little bit deeper and might need to adjust our forecast to include an area that, you know, we weren't expecting turbulence, but turbulence was there. And the way we do that is through pilot reports. So you can help us out a lot, and the entire aviation community, of course, by going and registering for an account on aviationweather.gov and becoming more knowledgeable with the correct information and formatting and the decoders for the pilot reports. And then you can submit those pilot reports right through our website there at aviationweather.gov/pilot/submit. And there will be two forms options, the full and the dispatcher form. So this is the full version, and this one just helps you out a little bit if you're not familiar with entering PIREPs. So it kind of helps you out, make sure that everything is decoded properly and correctly, so that when it comes into our system, we understand exactly what you're trying to say to us. And then the other form is just a dispatcher version, and this is for people that know what they're doing. They just want to get the pilot report out really quick and help us out. And all those pilot reports go to our website. They go to all of us into our weather database systems, so that it pops up and we can see what is happening almost immediately once you submit the report. And they're, like I said, they're incredibly helpful, something that we use every day. So the more the better for us. Okay, and finally, I just want to talk a little bit about the National Weather Service has a program called Weather Ready Nation Ambassador Program, and this is about readying communities for hazardous weather events. So organizations can become an ambassador, and by doing so, you're committing to helping your organization be prepared and respond to hazardous weather. So the goal of the Weather Ready Nation Ambassador Program is to have a nation that is ready, responsive, and resilient to hazardous weather. And it's a really great way to strengthen partnerships between us, the government agencies, the aviation community, and the users and the pilots. And we love our ambassadors, and we love our partners, and this is a great way for us to maintain that partnership and strengthen it. So if you'd like to know more about becoming a Weather Ready Nation Ambassador, just go to weather.gov/WRN. And with that, I think we'll move on to questions.
All right, good evening, everybody. I hope you've enjoyed the presentation so far, going over our organizational overview. So we've got Jimmy, Chelsea, and Amy are going to stay on here with me. We've got a couple questions, and so I'll go through what I've gotten so far, and the person who was in charge of that specific area, or maybe if any other ones want to jump in, they can do that. I'm Amanda Martin. I also work at the Aviation Weather Center. I've been there for 6 years as well. I also have previous weather forecast experience. I was at the Albuquerque Forecast Office for 5 years prior to coming to the AWC. Aviation was always an interest of mine, and it was just more whenever I got to the forecast office. So I'm really enjoying my time at the AWC, and I love forecasting for aviation and just how different it is from the public side. But anyway, we'll go ahead and get into the questions. So the first one is going to be for you, Jimmy. They're asking if any of the WFOs have forecasters dedicated to aviation, New York or Atlanta.
Yes, there are some of the bigger sites. I believe Chicago, Atlanta. I know they do have actual aviation that just dedicate to those jobs. Here, I'm at the Pleasant Hill WFO. I've had a little bit sick this week, so Joey was nice enough to do the briefing for me. But so there are some offices that do have aviation that's just dedicated to that. But at each WFO, we are assigned aviation depending on what your duties are that day. So when I go into work later tonight, if I take the forecaster shifts, I will be dedicated to aviation and then also all the other forecasting stuff. So it is one of the things you will dedicate yourself to when you do create the TAFs.
Thank you, Jimmy. We've got another one for you about TAFs, asking that they understand that some WFOs issue new TAFs more often than every 6 hours, even if amendment criteria isn't reached. Is it true? And if so, which offices are doing that?
I do believe some offices do it a little bit more. It's the bigger offices. I think it's Chicago, Atlanta, the ones that do the 30-hour TAFs that do that. But we're constantly watching the TAFs at every WFO, no matter where you're at. And if we see any of that criteria that you saw on that slide change, we will amend the TAF, and we try to keep that TAF as accurate as possible live. We're always monitoring the conditions at the different airports, and so if we see something go out of category, we will amend immediately. So that does happen.
And if I could just add, St. Louis is one office that does do a 30-hour TAF for St. Louis Lambert, and they have a mandatory every 3 hours amendment. So the bigger airports, the top 50 airports, top 30 airports are going to have more frequent amendments that are required.
Thank you, Jimmy and Chelsea. The next one, Amy or myself can answer, is where are the graphical forecasts for aviation produced? Amy, do you want to go ahead?
Okay. Graphical forecasts for aviation produced. I'm assuming the GFA or the graphics that we produce ourselves. The GFA is on our website. I don't know if I can share my screen, but if you go,
I can go ahead and answer that on,
okay,
on the question. But yeah, the GFA is produced at the AWC.
Yeah, it's produced at the AWC. But if you go to our website under hold on just a minute, under tools, the GFA tool is where you can find it on our website. But yes, that is produced through a plethora of model data on our website.
Okay. The next one I think will be good for Chelsea. It says, during a flight, when I give a PIREP to a controller, do they pass it on to you?
Absolutely. So I highly recommend giving pilot reports to controllers, especially if you don't have access in the cockpit to do it right then. That's part of the controller's duties. They're required to solicit and to disseminate pilot reports. So especially basis and tops reports, if you're going into an airport and you're talking to the center and they're doing approach services for that airport, they're actually required to solicit one basis and tops report every hour. And part of my job is to make sure that they know when we're meeting the criteria. Basically, it's below 5,005. So if any airport is below 5,005, they should be getting basis and tops reports. So feel free to give them your reports. And the nice thing about that is they're already staring at your information. They already know your aircraft type. They already know your altitude, and they already know your call sign. So all you have to do is tell them the weather. It's best to keep it brief, of course, when you're talking to air traffic control, but they can very easily enter that in. It goes to our flight data system, and they will process it and send it out to everybody. So we also rely very heavily on pilot reports, and we strongly encourage you to pass them on.
Okay, we've got a whole slew of questions coming in now. So I think we're gonna have to answer just a couple more in regards to the time. We're already a little bit over for our session, but we'll go ahead and see if we can get a couple more in, and then I'll try and answer them throughout. So the next question is, I don't really think we have too much on this one. They're asking about near future upgrades to the aviation program in general, CWSUs, AWC, new products or services, smoke tracking, and that the HER was valuable with the 2020 summer fire season. I think we're constantly working. Every year we have two times a year, usually we have our aviation weather test beds where we all come together from the AWC. We have our support branch, research and development forecasters. We have CWSU, meteorologists, weather forecast offices. We're all working on getting, pilots and our customers what they need. We just need to know what it is. So if you want to, send an email to our webmaster, we need to know what it is so that we can keep up. And we're constantly trying to make sure that we're getting the best product out to you guys. I don't know if you guys have anything else to say on that.
I think one of the biggest things from the CWSU perspective has been our new satellites that have gone up in the last few years, and the global lightning mapper, which is providing much more extensive coverage of lightning, both in cloud and cloud to ground and everything in between. So that's been really helpful for us, and there's going to be new GLM products that are rolling out to users, and you will be able to access more of that data very soon, and I think that'll be really helpful during the thunderstorm season.
Thank you, Chelsea. So let's see. Okay, so we have a question about flying in IMC and the biggest concern being thunderstorms, embedded thunderstorms. So we're gonna go ahead and hit that in the next half of the presentation that's going over hazards. So I'll save that one. Maybe we'll answer it next time. And let's see. Okay, sorry, you guys are coming in fast. I'm trying to read them all. So when will the legacy text AirMet be retired, given that GAirMets have been the primary issuance for over a decade? In fact, you can't find a graphical version of the time smeared text AirMet on the AWC website. So that's definitely been talked about a lot at the AWC. I don't know, Amy, do you have any, or Chelsea, any ideas on It's been talked about. I'll just say that.
What? I can't see the question. What was the question again?
Retiring the text AirMets.
Text AirMets. No, I think that's a requirement from the FAA to have those. So probably not anytime soon. We have the graphical AirMets too. So I think it's just, they're just auto, we don't type them out by hand. They're just auto generated. So.
Okay, so I'm going to go ahead and close out this first Q&A. I'm going to try and answer some of your questions that came in, just so that we can try and get a little bit back on schedule and get this thing continued. So thank you guys for your questions. Keep them coming in. I'll be watching them and trying to get them answered as fast as I can.
Yeah, thank
Jonathan?
you. Thank you.
Yeah, great. Thanks, Amanda, for that. I really appreciate the help on the Q&A piece, and thank you also, Amy and Chelsea and Jimmy, for answering some of those questions. So we'll have some contact information at the end of the presentation. So if there are questions that you have and we didn't get to it, then we'll certainly follow up with you. But so hang tight. We've got a lot of really good stuff coming up next. This will be session 2. This is more about the winter weather hazards. We've got 3 presenters lined up for this one. We'll talk about some icing, turbulence, sailing visibility, and precipitation concerns that you may have in the winter. Notice some of the questions in there coming in about icing conditions and whatnot. So we'll hopefully try to answer those. And again, if we don't get to it, we'll have contact information at the end, so you're more than welcome to follow up with us. So with no further ado, we'll get started off with Mitch Sego to take care of icing. Off to you, Mitch.
There, I should be unmuted now. Sorry about that. I was just saying that I've had a cold, so if I'm wheezing a little bit or coughing some, please bear with me. I should be okay for the most part, though. I'm Mitch Sego, and I've been at AWC here in Kansas City for about 3 years. Prior to that, I was up in Alaska in Anchorage, what is called the AWU, or the Alaska Aviation Weather Unit. And I spent just over 5 years up there. And then before that, I actually was in broadcasting. I spent a few years up in Anchorage on TV. So I've done a little bit with both sides, in front of the camera and behind. So, all right, next slide. So I'm going to be talking about icing, which sounds like we've already had some questions on this. Of course, can be a pretty potent threat. Here's a couple of pictures in case you haven't run across icing before. It gives a nice visual of what is going on, of some different icing types. And excuse me, on the left there you see an example of some rime icing, and I'm going to go through these in a little bit more detail on the next slide. Some clear icing. Looks like kind of an extra skin on the fuselage there in the center, and then kind of a chunky conglomerate, or maybe some freezing rain perhaps in this picture, and some mixed in the picture on the right. So let's get into talk a little bit about the different types of icing and some of the components with them. We'll head to the next slide. So as I said earlier, one that we see in most PIREPs is rime ice. This is a type of ice actually that occurs right around 70% of the time. It's the most common, and it's essentially where a water droplet freezes very quickly, and in doing so, it will trap air in it. And so when it hits an aircraft, it becomes more brittle and more opaque. It has kind of a milky color to it. Pardon me. But nonetheless, it can have some pretty big impacts. Clear ice is probably the bigger threat. Similar type of process, but instead of trapping as much air, the droplet will typically be larger many times, and it will smear across the aircraft. It's less opaque, therefore, and it can certainly be more dense. So that can be a severe threat if we see that. An example of clear icing is freezing rain. So, and of course, freezing rain is something you don't want to get in the middle of if you're up in an aircraft. Then we've got mixed combination of clear and rime icing. It can sometimes appear in different layers, so you'll get kind of an opaque look and more of a clear look. It accumulates light clear, but it's more difficult to remove than rime ice. So those are the three main types of icing. And let's see, we'll just head to the next slide, I guess. We'll keep this moving along here because I know we're short on time. Ice rates of accumulation range anywhere from a trace to severe. Trace typically not a big hazard. Any kind of de-icing or anti-icing should take care of it. Light icing, you'll occasionally see some de-icing needed. And if you spend enough time in it, say you fly through a layer where it's not a thick layer, but you're going right smack dab flying through it for an extended period of time, say for like an hour, it can accumulate up to a point where it can become more of a problem. Moderate ice, in a shorter time, of course, it can become hazardous. De-icing, changing your heading, altitude is typically going to be required. And of course, severe ice is the no good one. De-icing isn't always going to be able to help out, and an immediate change of heading or altitude is your best bet to try to escape if you get into a layer of severe ice. And again, freezing rain would oftentimes fall into that category of severe ice. Next slide. Excuse me. Synoptically, I'll go over this really quickly. Warm fronts can be a real problem area, and you might have some experience with that already. But if not, that's something to keep an eye out for. When you have a warm front, and this A to B cross section here, we'll kind of advance this through here of the freezing level line that kind of gives you an idea north and south of where the freezing temperatures are. And then let's advance one more if we could, just to keep this moving. Thanks, Jonathan. When you have a warm front, what you're often seeing is you're getting warm air that's riding up and over colder air closer to the surface. Now, when the whole column is cold enough or below freezing, below that 0 C, it's just going to be snow, of course. But you get anything beyond that, which is often the case in the Midwest and heading eastward, and you can get into different types of precipitation. So freezing rain, ice pellets, different kinds of things, and of course freezing rain is the big threat when it comes to icing. So where you see that red shading in there is where you would expect to see some freezing rain and some pretty good icing potential. North of the warm front and right along and into the cold sector, right along and just north of where the 0 C line is, the freezing line is. So that's a real trouble spot, and we see that quite a bit. There's other scenarios you can get along a cold front, but a warm front can be pretty prolific, and so it's something to keep an eye out for if you're going to be going up in the colder season. That warm front lifting up and out ahead of that to the north is where the icing can be pretty bad. Next slide. Excuse me. Some interesting data here. I'll just go over this real quickly from AOPA, their accident analysis. Over a 10-year period, 54 general aviation accidents were attributed to icing, and nearly half of those were fatal. This applies just to small aircraft weighing less than 12,500 pounds or less. Nearly 1/4 of all accidents due to airframe icing was caused by ice, actually, or frost that accumulated on the ground and wasn't removed before the takeoff. So that's kind of an interesting tidbit. That's an important component. Nearly 1/4 before they even got up in the air. And then, of course, to main parts or components, carburetor induction icing can bring down 3 times as many airplanes as just icing adhering to the skin of the aircraft. So that is also a big caution to be taken there. 2/3 of all fatal icing accidents are due to buildup on the airframe of the aircraft in flight. So still the majority, but just wanted to throw out some of these tidbits because they do remind us that icing can be a factor before you get airborne, and then of course once you're in the air, it can be. And it's not just on the fuselage or on the airframe of the aircraft. It can have other impacts as well to other components of the airplane. All right, next slide. So, excuse me. Some mitigation procedures that you can take. These are fairly straightforward, so I'll go quickly over them. Ascending into a colder layer, colder than 20 C. Typically, your icing potential is greatest from 0 C to minus 20 C. Excuse me, I forgot the minus in there. Minus 20 C. If you get below, certainly your icing threat, of course, drops off when you're above freezing. You get above that, you can still have some icing, but typically it's going to be on the light side to trace. So ascending into a colder layer, if you can, is typically the safest way to go to avoid any accumulation potential of further ice. Descending into a warmer layer below 0 C, also if you can, and that looks like the best route, is a good mitigation tactic to take. But you can sometimes pick up more ice. It sometimes is worse before it gets better. So that's to be used with a bit more caution than if you're going ascending up into a colder layer. And then changing your header, lateraling into a fierce scatter deck, and trying to bust out of a broken overcast is another way to avoid further ice. Just wanted to mention cold skin, where the aircraft is already very cold before you take off. This can delay the warming of the aircraft, of course, and make the aircraft more susceptible to icing as you increase in moisture once you get up in the air. So that's a mitigation to be aware of it all if de-icing is needed. Next slide. All right, we've already kind of talked about this some previously, but with SIGMETs and AirMets, won't go over them again a ton, but just to be brief, SIGMETs are a warning level product. So this is for severe conditions. They're issued and updated issued every 4 hours, updated if need be more than that. But those are to be taken pretty seriously for ice. I would say very seriously for ice. We don't issue a ton of SIGMETs for ice, but when we do, it's because we're really worried about a sizable area where there's going to be some severe ice, and that's to be taken very seriously. Zulu AirMets for ice. This is an advisory level product for moderate icing. It does include freezing levels in there, and that's issued every 6 hours. Next slide. And the last slide, I believe here, goes over the GFA. This is just to give you a look at if you're not familiar with it. The blue boxes on there, polygons rather, indicate where we have an AirMet out for ice. So you can see up over the lakes in the upper Midwest there, and then over the Northeast. You can play around with your forecast time. You can play around with the levels, which is really nice. If there's some levels that you're going to be flying through that you're most wanting to pinpoint, you can take a look at this tool. Handy, really handy, great for flight planning, great to just keep an eye on and get familiar with. So I encourage you to do that. And I guess I'll go ahead and close with that. We're going to head on over to Turb. So at this point, I will toss it over to Declan.
Okay, thanks a lot. I appreciate the opportunity to talk to everybody tonight about turbulence, some timeline constrictions, so we'll try to get through the material. Very quickly, just a look at my experience. Started back in 1981 as a marine routing meteorologist in California. And then from that point on, took an interlude of about 22 years of broadcast meteorology at the Weather Channel, also CBS affiliate in Birmingham, Alabama. And then after that, into the public sector, where I've enjoyed a very nice career in the National Weather Service. I've worked at the Weather Prediction Center in DC, went to Duluth, Minnesota for 8 years of wonderful winter weather, and now currently at AWC as a senior aviation meteorologist for 6 years. So let's go ahead and talk a little bit about turbulence. So just a kind of a quick definition: irregular motion of the air resulting from eddies and vertical currents. And of course, you know, the nice part would be the days that you have laminar flow, kind of equal wind field up and down and horizontally. But in most cases, that's just a pipe dream. As we all know, as we've been out there flying, turbulence is a lot more of a factor on any given day for some sections of the flight route. All right, let's see exactly how we can break this down, because we do have a couple of levels of turbulence, different types, and also intensities. Now, this is from the Aeronautical Information Manual put out by the FAA, kind of an attempt here to describe both from the terms of aircraft behavior and the in-cabin effect of turbulence, the intensity of such. And you'll notice we have on the left the scale: light, moderate, severe, and extreme. It's not out of the question. At times we'll see, working at the AWC, we'll get a PIREP with extreme turbulence, usually accompanied by a editorial comment. In many cases, perhaps heads hitting ceilings, whatnot. Not exactly the type of flight one wants to have, but there it is. We do also get reports, and people ask us, well, what's CHOP? You know, how does CHOP different from regular turbulence? And so what's going on with the CHOP is CHOP doesn't, let's say you have moderate CHOP versus just somebody reporting moderate turbulence. Well, by definition perspective, you'll notice here aircraft behavior moderate. There's a change in the altitude and or the attitude of the aircraft with moderate turbulence. With moderate CHOP, it's more likely that you're not going to see any significant change in either one of those parameters. So that's kind of the loosey-goosey of the difference between the CHOP. Again, if that does come up, that's what we're looking at. Let's go ahead and take a look at the next slide. So we're going to break this down a little bit here. There are several different ways that one can actually separate out turbulence due to diagnostics or causation factors, or with levels, let's say low versus high. We'll take a look at a couple of these in the interest of time constraint. We're not going to spend much time on the next slide, which is the convective aspect. This tends to be more of a seasonal summer parameter, but I just wanted to touch loosely on it. To the right, you see the diagram, which includes kind of the who's who of bad guys when it comes to thunderstorm development. Wind shear, quite likely at some time during the evolution of these cumulonimbus clouds. On the outer flanks, we can have debris picked up, so we could have visibility restrictions, outflow boundaries. We can have turbulence along the wind shear zones on those. We have roll clouds, even in the cirrus blow off. A lot of research recently kind of leading us to this idea that some of the older school rules of thought as far as what distances we should maintain for safety of the flight, those distances may have to be re-examined based on some of the latest research in the higher level aspect of these thunderstorms as the blow off emanates out, and we have what we call gravity waves. Literally something similar to, let's say you threw a stone in a body of water in a lake and you see the rippling effects. Same thing goes on. The atmosphere behaves just like a fluid in many respects. So we do have these little waves that emanate out from the updraft of the thunderstorm, and they cause these ripples and turbulence along these gravity waves. And that's one area where research has gone on quite extensively in the last 5 to 10 years. Next slide. Okay, so low-level turbulence. We'll talk more about that. And even though we are going into the wintertime mode and the sun doesn't have as much of an ability to stretch the boundary layer as much in the vertical, we still can encounter these. We have what we call the dry thermals during the daytime. It's simply the land is heated by the sun. The warm air above the land starts to rise, and we get these so-called thermals. They can be very significant if you've flown in the Southwest. The height of those thermals easily up over 14,000 feet. Mechanical forcing, we'll talk a little bit about that. Simply the flow that's obstructed or changed when it encounters surface obstacles. And a lot of the times with turbulence, the turbulence can be modulated or affected by several atmospheric parameters. How fast the ambient or the prevailing wind is, what kind of stability do you have that day? Is it a very unstable day? Is it a stable day? Fair weather pattern? And also one big factor, terrain roughness, can certainly impact the flight route. And typically this low-level turbulence is within the planetary boundary layer. So that's the area that's effectively heated by the ground during the daytime. But it becomes a big factor during takeoff and landing, especially for the smaller aircraft. Okay. So we talk about low-level turbulence. We can actually look at it from two perspectives: mechanical roughness of the surface, or the thermal aspect, like the surface heating, as I've mentioned. And both of these contribute to a modification of the wind field at the surface. You take a look at the diagram on the right. Notice the normal glide path that's illustrated in the solid line. Now, let's say you're on final and you're coming in on the top frame, and your route takes you over rocky terrain and plowed ground. So the surface heating characteristics of that type of land is certainly a lot different than, let's say, a body of water or even a wheat field. So those are the types of vertical or convective currents that could affect that glide path as you're coming in on your final. All right, our next slide is actually going to talk a little bit about the thermal turbulence. Typical scenario here from left to right as time goes on. The sun, as I mentioned, warms the ground. We get these little thermals, these bubbles of warm air that rise. But what you have to remember is it's not just simply a case of the warm air rising upwards. As that warm air rises, it creates a vacuum, so the air surrounding that has to come in and fill it, because the atmosphere is always trying to reach what we call homeostasis or equilibrium. And so in this constant rising and then replenishing of the air, that's when we get all these changing air currents. So even on a so-called fair weather day with rising cumulus clouds, there's still a certain amount of turbulence that has to be contended with. All right, next slide. So this is kind of a simple view here. If we have terrain where we have uneven surface heating, as I showed you, a body of water versus, let's say, a plowed field or a tarmac or a heavily urbanized area with lots of cement, those different heating rates cause different types of convective towers. And so as a result, across a given terrain here, you could actually encounter a variation in the turbulence. One of the more simple rules of thumb, and again, as we all know, a lot of times in meteorology, even in our numerical modeling, we're making assumptions to get to some final state or conclusion. This is the same scenario. You can get into the lumps and bumps, below cloud base in the rising air and certainly into the cloud. And then as you get above that cloud base, they tend to find a little bit of a smoother flight above what we call the cumuliform clouds. However, to keep in mind, now that's not certainly going to be the case. If you have a significant convective tower, then we could be looking at certainly a different scenario and a violation of that particular rule of thumb. Next slide. So mechanical turbulence. Description here, kind of simplified, but it gets the point across. On the left, you see airflow coming in from the left to right. It encounters a grove of trees, let's say, of a certain height. So the air is up and over, and then there's a kind of a tendency just downwind of the, let's say, the forest canopy, where we have a rotation of the air down to the ground. Now, let's just suppose that we increase the height of that blockage, in this case, the trees. Now, not only do we have the up and over effect, but you notice the circular kind of rotating air column there just to the lee or to the right side of that bigger tree. So this is the type of mechanical turbulence we talk about. And on the right here, you can see kind of an accentuated example of that, where we have two different sized buildings, ambient flow coming in from left to right. And again, just a whole variety of small-scaled circulation patterns and vertical and horizontal air currents that actually can affect the surrounding terrain, and in this particular case, certainly good aspect there on the runway. Next. So next I want to talk briefly about mountain wave turbulence. I wanted to show you the satellite picture on the right because it does a very good job of depicting this. And I mentioned earlier in the presentation this whole idea of the gravity wave, the ripples in a lake from a stone being thrown in. And again, so here we have airflow coming over the Appalachians. You can see that very wave-like characteristic satellite signature that we see. In many cases, this can be an indication that we could be looking at some turb, especially I notice a lot of times in this particular case, the Shenandoah Valley in Western Virginia, very prone to these wave-like motions from the mountain waves. Now, this is a kind of a smaller scale. Folks in the West like to joke about the eastern mountains as being just little hills. And in terms of elevation, certainly the case. You go to the west and in the Rockies, these mountain waves can extend to very high levels through the entire trope, even up into the lower stratosphere. We can get these gravity or lee waves at all altitudes, but in particular, especially in the east and also for parts of the Rockies and plains of Colorado, you can get these hydraulic jumps or these rotors that form just east of the mountain range. So certainly any type of mountain flying that you plan on doing, it's a whole new ball game because the ability of terrain to induce some pretty dramatic changes in the air characteristics is quite large. Next slide. Then we, of course, have a little more common maybe to a lot of people's perspective, frontal turbulence, warm air being lifted along that upglide slope that we just saw in the icing presentation with Mitch. Also commonly associated with cold fronts, particularly strong ones. The convection that can occur in the strong winds, typically ahead of an approaching strong cold front. All of these things can contribute to issues with maintaining control of the aircraft. Next. So here's an example of warm air, kind of a warm frontal situation. Going up in height on the left here, temperatures increasing with height as this is an inversion. And these inversions are very problematic in a kind of a narrow corridor. It's right along that interface where the temperature stops its rise, steadies, and then drops again as it typically would as you're going aloft. And what we'll find is that typically in the fall, this time of year, we get the nighttime radiational cooling, temperatures drop dramatically, warmer air and still more wind flow aloft, so things are mixed up better so it doesn't drop. And we end up with this thermal or temperature profile that you see here. And right along that inversion interface is where we have these eddies, and the wind shear can actually be quite significant, even in one of these, what we would normally consider just a general nocturnal radiation inversion. So that's certainly something you need to be aware of if you're flying at that time of the day. Also, one interesting aspect, when these inversions break, typically it takes a few hours for the sun to heat the ground to get things mixed up enough in the lower layers, but it's not uncommon that we can have a rapid fluctuation and a sudden gust of wind in, let's say, a 15 to 30 minute window when these inversions, what we call break, as the mixing starts to extend through a much greater depth of that vertical column. Okay, next. So the wind shear we talked about along these frontal zones, you can have in the vertical now, in all three examples here, you can see we can have the directional shear that occurs along these frontal boundaries. Speed shear, you don't have to have it. If you have significant change in wind speed in a very short distance with height, that's a big issue. And then in some cases, you get the double whammy where you have both a strong speed and directional shear. And all of these frontal wind shear patterns can certainly cause a lot of trouble for aviators. Next. So talk a little bit about clear air turbulence. Not as much of a factor if we're down below 15,000 MSL. Once you get above that, and especially now as we go into the winter season, flights above that level, we're looking very carefully in the vicinity of the jet streams, the tropopause, any upper level fronts. We can find these tend to be the neighborhoods where these clear air turbulence features hang out. One of the problems with forecasting turbulence, temporally, spatially, this is a very limited phenomena. As we all know, you're in an aircraft, you hit turbulence, it's here and it's gone, usually in a very short period of time. Almost akin to a needle in a haystack when you're trying to forecast these things. What we do know from the science part is that there are certain patterns that are conducive to producing turbulence. Having said that, doesn't necessarily it occurs every time that pattern presents itself, and that's the challenge to the meteorologist. These clear air turbulence features certainly can occur in the upper trope, even into the lower stratosphere. Thankfully, with the research that's been ongoing, we've had a lot more of, I guess, of the inroad into trying to forecast these things with a little more accuracy. Next. So aircraft-induced turbulence, so the wake vortex, mainly a concern, of course, near the airports. If you're trailing a big guy, you got a heavy taking off in front of you, and I think everybody involved in aviation learns that pretty quick. But we can still get a significant number of these encounters that can occur at the upper levels as well. And so go ahead and roll that video. I think if our magnificent production crew can go ahead and give us this. Now, this is an exaggerated, we've got a big C5A, I believe it is. We got the smoke set up on the layers in the vertical along that tower, and then we can see a pretty dramatic colorized version of the wake vortex. But again, same phenomena that you're going to encounter if you're trailing a heavy and you're coming in on your smaller aircraft and you've got these wake vortexes or wake vortices, certainly can be a big factor in control of the aircraft. All right, thanks for the video. And I believe we have another slide, the last one. This will be, okay, where can you get some turbulence information? Now, the good thing is here, this is the GTG, the Graphical Turbulence Guidance. This has been an ongoing effort since 2003. So we're up at like year 17 in the development of this product. A very good, I would strongly recommend you take some time, like a lot of meteorological products. It gets better as you spend more time with it in terms of you getting comfortable with how to use it. The first few times, maybe a little rough. You can pick your aircraft type there on the left. In the case for most of us tonight, I believe, that's going to be light. And then what you do is you pick your vertical level of interest or interest if you're going through several layers there and you want to check each one out. And this actually has the ability, you can break it down to clear air or mountain wave. It used to be in the earlier iterations of this software that it would only handle certain layers above like 15. But since the last 5 years or so, there's now a much better product that's able to detail this down to much lower levels. You can go from 1,000 to flight level 45, 18 hours forecast that'll go out. It's updated every hour. It runs off what we call the RAP model, which incorporates the latest satellite, radar, and also more importantly, it's taking in all the latest pilot reports and using that to nudge or adjust the ongoing model run to better fit the reality. So it's a very good product. I strongly recommend that you take the chance or take the opportunity to go in, look at it, and you'll notice like a lot of our products in the upper right, there's an info button. You can toggle on that and it'll give you the complete lowdown. It's quite sophisticated because we've got actually different parameters that we look at. We call them diagnostics, but there's different ones for different layers of the atmosphere. So it's not just one big broad brush paint for the whole surface to 45 layer. It's broken down to where it intelligently assesses the layers based on our latest research as to what is most important in that particular layer. And I believe that's the end for me. Apologize for the rapidity of the presentation there, though, but in the respect of time, I wanted to give Joey a chance. And also, of course, anytime you can just give us questions, email me, and I'll be glad to answer any of your questions. Joey?
All right, well, thank you, Declan, and thank you for hanging out with us thus far. I know we've gone a little over, but I am the last section. Then we'll have a quick Q&A, and we'll be wrapped up. I do want to talk briefly on ceilings, visibility, and precipitation, specifically when it comes to winter weather and some of those hazards that you can encounter over the next several months. Go ahead, next slide, please. So we'll take a look at ceilings, what forms clouds, how that whole process commences in a nutshell. Basically, we won't go into cloud physics or anything like that, but we'll look at what are the determining factors for reduced visibility and ceiling heights. Basically, the cloud base or ceiling height is determined by the height in which air condenses and becomes saturated. In a nutshell, rising air cools to the point of condensation, and if you have enough rising motion and enough moisture vertically stacked, a variety of cloud types will form over a given area. You can think of this in terms of stratiform cloud types versus convective cloud types in two basic forms. Cloud types are also dependent on seasonality, geographic location, and atmospheric locations, or atmospheric conditions as well. Slide, please. So if you take a look at this example, this is from Grand Forks. You can see the METAR there. Shows a broken cloud layer at 7,000 feet. It's important to note that any ceilings that you see in METAR data are reported in AGL, above ground level. So in this case, the cloud base is actually at 7,845 feet mean sea level. Once we factor in the field elevation of 845 feet, we get the broken at 070 that you'll see in the METAR. Next slide, please. And one of the tools that we use to forecast ceiling heights are going to be the QT diagrams. A lot of you have seen these. I think I saw a question about that in the chat there. But basically, they depict a vertical profile of temperature and dew point trends. Here you can see the red line representing temperature, the green line, of course, representing dew point. There's a lot of other data that's depicted here, but for the sake of time, we'll just talk about temperature and dew point. In this particular case, we'll see a saturated layer pretty low, roughly between 5,000 and 7,000 feet. And this is the kind of data we look at to determine ceiling heights. We can also look at this data in hourly increments with high-res guidance, which is invaluable for forecasting trends and ceiling heights over a given location. And again, this represents a point, so it's not a big spatial outlook of trends, but we can look at many different points to see what the trends are, to kind of time the arrival of lower ceiling heights, that kind of a thing. So this is an invaluable tool for us, and a lot of our TAF forecasts in aviation products come from this type of model data. Next slide. So let's switch gears and speak briefly on what factors come into play with reduced visibility, namely fog and precipitation for this discussion. Fog's a pretty complicated beast. It forms in different ways. Here are a few examples of how it typically forms. In our first case here, radiation fog is probably what you're going to see in most cases. It basically forms from heat stored in the Earth's very shallow layer at the surface that radiates upward at night. This in turn cools the layer just above the surface until the point it reaches condensation. This is most common on clear nights, oftentimes right after precipitation exits the area, high pressure builds into the area, so you have a very moist surface. Once you start cooling that, you saturate pretty quickly. The next example is common in terrain with upslope fog. It develops basically as a stable, moist layer, slowly moves over terrain and is forced upward. And the same thing happens. It reaches condensation and begins to saturate that area. And finally, advection fog forms when a moist layer moves into a cooler environment over land or water. In the Kansas City area, interestingly enough, this is most often occurring when you have southerly winds advecting into an area where snowpack is present. Usually you have to have an inch or more of snow on the ground, but it's pretty neat to see terrain, the surface covered with snow, and then all of a sudden you've got fog developing over the area, and it actually helps to melt the snow. But that's advection fog in a nutshell. Next slide, please. And the final cause for reduced visibility and/or ceiling heights is going to come in the form of precipitation and precipitation type, particularly as we head into the winter months. So precipitation type, as you know, it's critical and can be difficult to forecast given the multiple factors at play. It's not black and white as liquid precip is. So let's look at the difference in precipitation types to see what's going on and what causes everything in the spectrum from rain to a wintry mix all the way to snow. So if you look on the far left, a lot of you guys have seen this graphic before, but this kind of generalizes a lot of this, but it does help to explain what's going on thermally. So if you look in the far left, you'll see the very simple case of all rain. This basically occurs when you have a very sufficiently deep warm layer where any frozen precipitation melts and remains melted, and it reaches the ground as liquid precip. Going over to the next example, you have a sufficient warm layer that is able to fully melt any frozen precipitation, but then it goes back into a sub-freezing layer near the surface, and you basically form super cooled water that freezes on contact with any surface objects. Going a little bit further to the right, we still have the warm layer present, kind of complicating things. So you have frozen precip that partially melts and then fully refreezes in that sufficiently deep sub-freezing cold layer. And it forms sleet. And of course, you've got ice accumulation just the same as you do freezing rain at the surface. And then going back to the simpler scenarios, anytime we have a completely below freezing column, we have all snow, and that's obviously not going to accumulate ice unless you have above freezing surface temperatures initially. But you know, as you're flying, it's not as simple as what you'd see at the surface. You can quickly go from one regime to another, and you can actually fly through these processes as they are happening, and you can quickly get ice buildup, like Mitch was talking about earlier. So it's certainly worth keeping an eye out for when you're flight planning to keep in mind any areas of, you know, mixed precip or a transition area that you're going to be flying through, because what you see at the surface is not always what you get at the upper levels. Next slide, please. So with freezing rain having significant impacts to aviation operations, this is a quick display of a study from 2003 showing the frequency of freezing rain events over the U.S. The number of days may be a little bit hard to see, but in the northern and central plains, especially across the Northeast, freezing rain events typically occur anywhere from 3 to 7 days in a given winter season. And obviously this can wreak a lot of havoc to aviation operations. These are only averages, and numbers may be much higher for a given area in a given winter season. Next slide, please. And we'll take another quick look at visibility reductions during winter precipitation, which are directly related to precipitation intensity. Intensity is going to be dependent on the amount of rising motion that you have and the amount of moisture supply that you are given over a particular region. And typically speaking, we can kind of generalize here, and this changes a lot, but you know, in a given hour, but typically speaking, light snow reduces visibility down to 2 to 3 miles. But as soon as you get into the heavier snowfall, you can reduce visibility down to 1 mile or less. And it's important to note, you know, for flight planning purposes, you can always use TAFs at your departure and arrival locations to anticipate visibility trends and expectations. Some airports, especially smaller airports, may not have a TAF issuance at all, but you can use nearby airports, you know, to kind of get the feel for, you know, expected trends over that given location. And I believe that's all I have. Next slide. And we will turn it over to Amanda one more time for some more Q&A.
All right, thank you guys for sticking with us through the second session. If I could get Joey back up here, Declan, I see Mitch is already on. In the interest of time, I'm just going to give you each one, and then the rest, we'll go ahead and put up a slide after this that shows emails, and you can go ahead and email your questions there, and we can answer those. So Mitch, I've got one for you regarding mixed icing and what conditions will typically produce that mixed icing scenario.
Excuse me. So, I mean, maybe others can chime on this as well if they have any input on this. As best I could explain it, a mixture, you can get different conglomerates of precip types. supercooled droplets, and then you get into different, thermal regimes. Typically, it's going to be kind of a more uneven atmosphere thermally, where you're getting different types of either precipitation or supercooled water, different sizes of that, freezing rain, of course. Trying to think of anything else. I don't know if anybody else wants to chime in on that, but that would be kind of the simple way that I'd answer that.
Yeah, I think the whole spectrum of supercooled liquid and how it evolves and behaves in terms of the ice nucleation process is a conundrum, but I would think the variation between, let's say, rime and clear or mixed rime and clears is just that combination of microphysics within the cloud or supercooled liquid layer on any given day.
And I would note it's tough for us we don't forecast. We forecast for icing potential and the threat with it, but we don't differentiate when we're drawing our air mets and all that and issue our product. We don't pinpoint on the areas of all those 3 different icing types. That gets into really murky water that we just.
I can step in and kind of help out a little bit. In the Air Force, when we would do icing, we would have to do the type as well with forecasting. And typically what we would look for is icing conditions between -8 and -15 Celsius. So when you get into that temperature range, that was typically what we would utilize as forecasters to say mixed as opposed to rime or clear. So that's what we used to use.
Thank you, Mitch and Jimmy, for answering that. Next, I'm going to give one to Declan. It says, the rule of thumb I heard years ago, crosswinds over mountains in excess of 20 knots tend to produce significant and building turbulence, like rotors, for example. Is that still a good one?
Like a lot of attempts in complicated sciences to come up with rules of thumb, it can be valid, but with a big caveat that it's not just the wind flow over the terrain, but also the direction, the more perpendicular to the flow, the more enhanced the ability. But all of this, the wind, mechanical obstruction, generation of the currents is all being, it's all occurring in an envelope of the atmosphere, and it's the stability or the instability at that particular time that allows the wave to then take on its characteristic result. So I would say in direct answer to the question, generally as forecasts of turbulence, when we're looking at low-level turbulence, we actually look at 25 knots, maybe a little higher. So 20 knots is probably okay to be on the cautious side, but again, 25 knots or higher, especially if it's perpendicular to the actual terrain orientation, I think is kind of the way you want to go. But again, a lot of this is also dependent on the stability characteristics of the atmosphere that given day.
Thank you, Declan. Okay, and we'll go ahead and give this one to Joey. When hearing surface, how high above ground level does the surface go to or is considered?
Anywhere that you're located on the ground is representative of surface. It's something we have to keep in mind for mountainous areas because the freezing layer in western Kansas may be 7,000 feet, but as soon as you go into Colorado, now you're above the freezing layer. So I don't know if I'm understanding the question exactly, but it's when we refer to the surface, we're referring to AGL, regardless of MSL.
Yep, I think that was it. So there's a couple more questions. I think we'll go ahead again in the interest of time. You guys can email us. I'm seeing a lot of thank yous as well. And thank you guys for coming. I'll let Jonathan close us out, but I'll go ahead and we'll let Jonathan finish us off, and we'll answer questions. And if you guys have any other questions, go ahead and email. All of our information is there.
Awesome. Thanks, Amanda, and thanks to the session 2 presenters. Really appreciate your insight, and we're going to try to capture all the questions that are flowing into the chat room. It's really awesome to see your interest level in what we're doing here, so we really appreciate your attendance. I would like to acknowledge a few folks who helped make this a success for us. Again, key leaders, appreciate Evan Doss and Chris Irish for working with us, helping us launch this endeavor. It's been a vision of ours to really increase the outreach in the Kansas City area, and we're kind of uniquely positioned having 3 different aviation offices, kind of the triad of aviation in KC. So it's really cool that we can partner with you to do this. So I really appreciate your support there. You can follow them on Facebook. There's their address. I also like to throw out a big shout out to Ron Moyers. He's an executive officer at AWC. He's also a NOAA Corps pilot, and he's been helping us out with some of the behind-the-scenes work. Jimmy, thank you again from WFO Pleasant Hill. Appreciate your time there, and also Jennifer Zeltwanger, who's the meteorologist in charge over at the City of Issue in Olathe. So I appreciate your support, and also Ryan Solomon, who's a science and operations officer at AWC, working some behind the scenes. If you'd like to follow us on social media, there's our handle. We're very active there as well. Amy and Amanda do a lot of great work there, and appreciate your comments and any questions that you might have for us. We'll certainly follow up with that. So again, thank you very much for your time tonight. We are a little bit over scheduled, but that's okay because we always believe in flight safety, and getting you the best information is our most important job. So with that, we'll close out for tonight, and have a great evening. Thank you very much for joining.